Hey everyone, and welcome back to Talk Tensors. Today we're diving into a brand new paper.
Oh, very exciting.
Yeah, super interesting stuff. It's called Entangled Mean Estimation in High Dimensions.
Okay.
And it just came out this month, actually, January 2025.
Wow.
So hot off the press.
Yeah.
Have you ever felt like you're just like drowning in data? You're like trying to figure out what really matters?
Oh, yeah.
Like,
Absolutely.
what's the signal and what's the noise?
All the time.
That's what this paper is all about. It's about finding the average, the mean,
Right.
in a whole bunch of data where like every single data point has its own lever of noise.
Okay, yeah.
Or like
Yeah.
uncertainty,
Yeah.
right?
Yeah.
So it's kind of
Like, how do we sift through all that to find
what's really going on.
yeah, the real average, like the signal amongst the noise.
Exactly. So like imagine you're trying to find the center of a swarm of bees,
Oh, okay.
but like some of the bees are super jittery and some are calm.
Some are like, yeah.
How do you like actually
Right.
find the center of that?
Yeah, that's a great analogy.
And this isn't just some theoretical thing
Right.
that like mathematicians are thinking about.
Right.
This has like tons of real world
Real-world applications, yeah.
implications. Yeah.
Yeah.
So think about crowdsourced ratings,
Okay.
like on different websites, different users have like different expertise.
Different levels of, yeah, sure.
So how do you count for that?
Yeah.
Or like sensor data that's collected in all sorts of different environments.
Right. With varying levels of interference.
Totally. So like, how do you like,
yeah. How do you know which sensors to trust more?
exactly.
Other.
Exactly. And even like financial markets where volatility is like all over the place.
Yeah, absolutely.
It's like, how do you find the true
signal. Yeah.
the true signal
Yeah.
amidst all that chaos?
It's essential for making good decisions.
Totally. So this paper is really exciting. It's got a lot of cool ideas in it.
It does.
So to like really understand the breakthrough, I think it'd be good to like rewind a little bit
Okay.
and look at how like researchers have approached this problem in the past.
Yeah. How did we get here? What's the history?
Totally.
Yeah.
So
Well, the early attempts, focused on a simpler version of the problem.
okay.
The one-dimensional case.
All right, so like
Much easier to visualize and wrap your head around.
okay.
So imagine like you have a bunch of thermometers.
Mm-hmm.
Some are accurate. Some are wonky.
Okay.
And you know that like a certain percentage of them are reliable, but you don't know which CH ones.
Ah, so you have a mixed bag.
Right.
Oh,
You just don't know which ones are good, which ones are bad.
gotcha.
But you still want to get a good estimate of the true temperature.
Okay.
That's the challenge.
So it's like,
You have a mixed bag of tools.
yeah,
Some are sharp, some are dull, but you got to get the job done.
yeah, and like figure out how to use them.
Exactly.
So-
And that scenario, that's essentially the subset of signals model,
Oh, yeah.
which Lai and Ye introduced back in 2020.
Okay, so they kind of formalized this problem.
Yeah, they put it on the map
Okay,
and said, hey, this is something we need to figure out.
interesting.
And then a major breakthrough for this one-dimensional case
Uh-huh.
came just last year, actually,
Oh, what?
with a paper by Chen and Valiant.
Yeah.
They developed what's called a near-optimal solution,
Okay.
which means it's incredibly accurate
Uh-huh.
and efficient in finding that true temperature, even with those wonky thermometers mixed in.
Oh, that's cool. So they found like a really good way to do it.
Yeah, a really good way to do in one dimension.
Okay, but the real world
Yeah.
is never that simple.
Rarely one-dimensional.
Right. Data is almost never just in one dimension.
Exactly.
So how do they go from that one-dimensional case to like higher dimensions?
That's where things get really interesting
Okay.
and a lot more challenging.
All right, let's take a quick break and we'll come back and dive into that.
Sounds good. So yeah, going from one dimension to higher dimensions,
Yeah.
it gets a lot harder.
Okay.
So imagine instead of just thermometers,
Mm-hmm.
you have sensors that are measuring like temperature,
Okay.
humidity, wind speed, and air pressure all at once.
Oh, so now we have a lot more.
Now you're dealing with a four-dimensional problem.
Okay.
Yeah.
Yeah.
And as you increase the number of dimensions,
Mm-hmm.
there's just so much more space for the noise to like mess things up.
Ah, so more dimensions equal more chaos.
Essentially, yeah.
Yeah.
It makes it much harder to find that true average.
Gotcha. So did those earlier approaches, like the one from Chen and Valiant,
Right.
did those still work in these like more complex scenarios?
Not really.
Oh.
So simple averaging, where you just like sum up all the points and divide,
Yeah.
fails miserably
Okay.
when you have this kind of multi-dimensional noise.
Right, because you're averaging in like all these different dimensions. So like,
Right. You're not accounting for the fact that the noise might be different in each dimension.
yeah, gotcha.
And then trying to apply that efficient 1D solution
Mm-hmm.
to each dimension separately,
Yeah.
that becomes super inefficient.
Okay.
It's like trying to solve a giant jigsaw puzzle, but like focusing on each tiny piece in isolation
Yeah.
without considering the bigger picture.
Without seeing how they all fit together.
Exactly.
Yeah, okay.
Yeah.
So for a while, there wasn't really like an accurate A&D efficient
Right.
solution for this high-dimensional problem.
It was a major open question in the field.
Oh, wow.
Even Jerry Lai, who's like one of the leading researchers in this area,
Okay.
highlighted this challenge at a workshop a couple of years ago,
Okay.
calling for new approaches.
Wow. So this was like a big problem that people were trying to figure out.
Yeah, this is like the holy grail of entangled mean estimation.
Okay.
And that's where this 2025 paper that we're talking about today comes in. They've managed to kind of crack the code.
Okay, now I'm really intrigued.
Yeah.
So can you walk us through how this new algorithm works? Like, what's the secret sauce that makes it so effective?
All right, so it's a multi-step process, kind of like a detective, meticulously piecing together clues to solve a mystery.
Oh, I like that.
All right, so the first step involves what you might call a tournament.
Okay, a tournament.
Yeah.
Interesting.
So imagine you have a bunch of possible guesses for the true mean.
Okay.
All lined up, ready to compete.
So like a battle of the means.
Exactly.
You love it.
And these guesses are pitted against each other.
Okay.
Using some very clever comparisons that are based on projections of the data.
Projection. Okay, can you explain that a little bit?
Yeah, so think of it like shining a light
Okay.
through a complex object and seeing its shadow.
Okay.
That shadow is like a simpler, lower dimensional representation of the object that's easier to analyze.
Gotcha. So it's like simplifying the problem a little bit.
Exactly.
By looking at these projections.
Yes.
Okay.
And so in this tournament, the winner of each round gets to stay in the game.
Okay.
Right? And the losers get eliminated.
So they're eliminating bad guesses early on.
Precisely.
Without needing to analyze every single data point.
Exactly.
That sounds efficient already.
It is very efficient.
Okay.
And this process very quickly narrows down the possibilities and gets us closer to the true mean without having to do these like brute force calculations.
So it's like a smarter way of searching.
Exactly. A much smarter way of searching.
Okay.
But now you might be wondering, what happens to those losing guesses?
Yeah. Are they completely out of the picture?
Not quite.
Okay.
They play a very crucial role in the next step.
Okay.
Which we call the cleanup crew.
The cleanup crew. All right. Now you've got my attention. Tell me more.
So the cleanup crew, they use the winning guess from that tournament we talked about to filter out the really noisy data points.
Okay.
Think of it like shining a spotlight on the data.
Okay.
And any points that are too far away from that spotlight, we just toss them out.
We're like, okay, you're
you're probably too corrupted by nulls.
Yes, you're too far out there.
You're not reliable.
Yeah.
So we're going to get rid of you.
Okay, so we're like refining the data set as we go.
Exactly.
So what happens next?
Now, this is where it gets really interesting.
Okay.
The algorithm takes these remaining points.
The more reliable ones.
The more reliable ones. Yeah. And it finds this special region, a subspace.
Okay, a subspace.
Within the data where the noise is much lower.
A low noise hideout.
Exactly.
I like that, within the data.
It's like if you're in a bustling city.
Okay.
With noise coming from all directions.
Yeah.
And you step into a quiet park.
Oh.
Where the noise is just dampened.
So there's like a little pocket of calm.
Exactly.
Within all the chaos.
So the subspace, it's like a lower dimensional slice of the data.
Okay.
Where the points are clustered more tightly and the impact of the noise is like significantly reduced.
Okay. I think I'm starting to get it.
Good.
So by finding this like pocket of calm, we can get a clearer picture of what the true mean is.
Exactly.
Okay.
And so the algorithm projects all the data onto this calmer subspace, which makes the mean even easier to estimate.
Okay.
But here's the kicker.
Yeah, what's the kicker?
It doesn't stop there.
Oh, there's more.
It repeats this whole process.
The tournament and everything.
Tournament, cleanup crew, find a new hideout.
Wow, so they run this multiple times.
Multiple times.
Why do they do that?
So each time they repeat the process, they shrink the problem down, making the noise less and less influential.
So each time we're like getting closer and closer?
Closer and closer.
To the true mean?
It's like zooming in on a blurry image.
Okay.
And with each zoom,
the
picture gets sharper.
Oh. That's a good analogy.
And the true mean becomes clear.
So it's like a multi-stage rocket.
I like that.
Kind of propelling us towards the target with like increasing precision.
Exactly.
Every stage we get a little bit closer.
Exactly.
Right.
And eventually the problem is shrunk down enough that they can use that super efficient 1D solution that we talked about earlier.
The one from Chen and Valiant.
Yeah.
Okay.
That's the final touch.
Okay.
Applying that 1D magic to get a really precise answer in high dimensions.
Wow, this algorithm is like incredibly clever.
It's pretty amazing.
Combining the tournament,
Yeah.
the cleanup crew,
Uh-huh.
the search for the lore noise hideouts.
Yeah.
It's like a well-coordinated team tackling this problem from all angles.
It is. It's a beautiful symphony of algorithms working together.
I love it. But is this just some like fancy theoretical trick, or does it have real-world application?
Oh, no, this has tons of real-world applications. Anytime you're dealing with noisy data, where you suspect that some of it is more reliable than others,
Okay.
this approach could be a game changer.
So this isn't just an academic exercise.
No,
This could like revolutionize how we analyze data.
absolutely.
Wow. Okay, so can you give us some concrete examples to illustrate how this could be used?
Sure. So let's start with something familiar. Crowdsourced ratings.
Okay.
Imagine you're building a platform for rating movies, books, restaurants.
Uh-huh.
You have tons of users,
Right.
each with their own biases and levels of expertise.
Yeah, some people are 5-star fanatics.
Exactly.
Some are very nitpicky.
Yeah, you got the whole spectrum.
Yeah.
And so this algorithm allows you to more accurately estimate the true rating of a movie,
Oh, wow.
even with all that variation in user expertise.
So it's like you're filtering out the noise from like
Exactly.
the less reliable ratings.
We're weighting the opinions of users
Huh.
who have consistently demonstrated more discernment.
So it's like you're learning to trust certain users more.
Yeah, based on their past behavior.
Based on their past rating.
Exact
Oh, that's
steps.
really cool.
And it helps you sift through all those ratings and find the hidden gems.
I love it. What about applications beyond user ratings?
Sensor data is another area where this really shines.
Okay.
Imagine a network of weather sensors spread across a city,
Uh-huh.
each measuring temperature, humidity, wind speed.
Okay.
Some sensors might be affected by local conditions.
Like shade from a building or something?
Exactly. Or like a flock of birds landing on them.
Feathered interference.
Exactly.
Always a challenge.
Always a challenge.
Favorite data collection.
But with this algorithm,
Uh-huh.
you can account for those variations in sensor reliability.
Okay.
You can identify which sensors are providing the most accurate readings.
So you can like really build a robust and accurate picture of the overall weather pattern,
Precisely, even if some of your sensors are having a bad day.
even with all that noise.
Yeah, this algorithm is all about finding the signal within the noise,
I love
regardless of the source of that noise.
this paper is like
Yeah.
amazing.
It's not just about a specific algorithm.
Yeah.
It's about a fundamental shift in how we approach data analysis.
Oh, tell me more about that.
So for a long time, we've focused on eliminating noise entirely.
Right, like get the data set as clean as possible.
As clean as possible.
Yeah.
But this algorithm shows that we don't need to be afraid of the noise.
Wow.
We can learn to work with it,
Embrace the noise.
embrace the messiness of real-world data,
Yeah.
and still extract meaningful insights.
So it's like those imperfections and variations.
Yeah.
They actually contain valuable information
They do.
if we know how to listen to them.
Exactly.
This has been an incredible deep dive.
It has.
We've gone from thermometers and bees to social networks and weather sensors.
It's been a wild ride.
Who knew that finding the average in noisy data could be so profound?
It's amazing what you can find when you start digging into these problems.
Before we wrap up,
Yeah.
I want to encourage all of our listeners to check out the full paper.
Please do.
We'll link to it in the show notes.
Absolutely.
And if you have any thoughts on this algorithm,
Yeah.
or if you come up with any cool novel notions of your own,
We love those.
we'd love to hear them.
Yeah.
So you can connect with us on our website or on social media.
Until next time.
Keep those tensors talking.
And keep embracing the noise.
Yeah.